a problem based on Hartnell governor. So let's consider this problem. A Hartnell governor having a central sleeve spring and two right-angled bell crank levers moves between 290 rpm and 310 rpm for a sleeve lift of 15 mm. The sleeve arm and the ball arms are 80 mm and 120 mm respectively. The levers are pivoted at 120 mm from the governor axis, and the mass of each ball is 2.5 kg. The ball arm is parallel to the governor axis at the lowest equilibrium speed, and we have to determine the loads on the spring at the lowest and the highest equilibrium speed and the stiffness of the spring used. Okay. Now, first we will write the given data, the problem. So we'll write the given data. Now here there are two speeds. One is the minimum speed and the second one is the maximum speed for our governor. Say N1 is the minimum speed, which is 290 rpm, and N2 is the maximum speed, which is 310 rpm. Okay, and the sleeve lift, that is the value of H, is 15 mm. It is the displacement of sleeve when the governor moves from minimum speed to the maximum speed. The sleeve arm and ball arm are 80 mm and 120 mm respectively. So the sleeve arm and ball arm is X and sleeve arm is Y. So X is ball arm, that is 120 mm, and Y is sleeve arm, which is 80 mm. Okay. Levers are pivoted at 120 mm from the governor axis. The pivot of lever is 120 mm from the axis of governor. So let's consider this yellow line represents the axis of governor. Okay. And bell crank lever has two arms. One is 120 mm and second one is 80 mm, and it is pivoted here. This pivot point is represented by point O. This is our X, our Y, and the distance of O from sleeve arm from the axis of governor, this, which is 120 mm, length of this arm by 80 mm. So this distance is 40 mm. Okay, this distance is 80 mm. Distance is 1. Here we place the ball having mass m, and the mass of ball is given here is 2.5 kg. 0.5 kg. The weight of sleeve is not given here. The weight of sleeve is not given here, so we can neglect it. Okay. Now we know that relations of the first speed conversion, that is radian per second omega, corresponding to this n1 value and this n2 value. First we will calculate omega 1 and omega 2 values. Okay. So omega 1 on the basis of 2 pi n1 by 60, and omega 2 using the relation 2 pi n2 by 60. After calculations, these two values of omega 1 and omega 2, omega 1 is 30.4 radians per second, 30.4 radians per second, and omega 2 is 32.5 radian per second, 32.5 radians per second. These are the two values of omega 1 and omega 2. And if we know that the mass of ball is m, which is 2.5 kg, then we can also determine the centrifugal force acting on the governor ball is m omega 1 square into r1. Now we can know that this is the minimum speed configuration of governor, because here the ball arm is parallel to the governor axis at the lowest equilibrium speed. That means this represents the lowest radius of rotation r1 corresponding to the lowest equilibrium speed n1, and this is equals to 120 mm, and by converting it into the meters, it is 0.12 meters. And if I substitute the value of omega 1 r1 and m here, then we can easily calculate the value of fc1, and similarly we can calculate the value of fc2. This m omega 2 square r2. After calculating these values, we get fc1 as 277 newtons, and fc2 is 376 newtons. 376 newtons. These are the two important values to solve the problems. Okay, I will close these values to a rectangular box. We will use these values. Now we also know that the relationship between the sleeve lift and minimum radii of rotation and maximum radii of rotation and x and y, which is here in this equation number 3. So in this equation number 3, we know that the relation between h, r, y and x. So I will take this relation. We know that h equals to r2 minus r1 by 2 minus r1 by x into y into, after substituting these values here, r2, the maximum radii of rotation is at 310 rpm, R1, the minimum radii of rotation, we know that the value of minimum radii of rotation is R1, but we don't know the value of R2. So R2 is here as it is, minus R1 is 0.12 meters x y is 0.08 divided by 0.12. In this relation, the R2 is not given here. Don't know where the value of R2 is. We will search value of R2. Now, to find the value of R2, that is the maximum speed configuration of this Hartnell governor. Now, in maximum speed, during maximum speed, the sleeve will lift by 15 mm. That means this point will lift by 50 mm and this lever comes in this orientation. Now, I will draw a new configuration diagram on next page here. The axis of governor, the old configuration, okay. This is the new configuration. Since old configuration, this lift is 15 mm. This length remains same, 80 mm. This movement of ball I don't know. This distance I don't know, 120. So from these two triangles, you can easily determine the value of displacement of sleeve is 15 mm, the sleeve lift h, and can find the value of A. And if we are able to find the value of A, so final up your R2 becomes previous radius of rotation, that is R1, plus the new displacement, say A. Now we will determine A. So to determine the value of A, we can consider these two triangles, this first triangle, second triangle, and from these two triangles we can write the perpendicular side, the distance A, the ratio of these two sides, that is A divided by H, is equals to this horizontal side length, that is Y, and X. So X by Y. The ratio of corresponding sides, A by H, is equals to X by Y. So A is equals to X by Y into H. You can easily determine the value of A. That is, X is 120 mm and Y is 80 mm. H is 15 mm. So the value of A is 22.5 in mms. If I substitute this value here, so R1 is 120 plus 22.5 is equals to 142.5 in mms. So definitely in meters, 0.145 0.25 meters. This is the value of R2, and this R2 is substituted here to determine the value of FC2. Okay, so before determining this value, we have to find the value of R2, but here I will directly write here that the FC2 is this 376 newtons. Okay, now using this relationship of H, R2, R1, Y, X, you can also determine the value of R2 because H is given, and you can also determine the value of R2 using this configuration settings. Okay, now value of R2 is known to us. Now we have to determine the forces or loads on the spring at the lowest speed and at the highest speed condition. Now we have to draw the free body diagram of the configurations for the lowest speed as well as for the highest speed. Now this is the configuration diagram for the lowest speed and the configuration diagram for the highest speed. Okay. I will take figure directly. Now see, these are the configuration diagrams for lowest position and the highest position, that is for corresponding to the lowest speed and corresponding to the highest speed. Now consider this diagram first. This is for lowest speed. In this diagram, we can see here, this is the pivot point O. Okay, and the force acting on the ball in outward direction, which is FC1, there is the centrifugal force which we already determined that 277 newtons. Now at the sleeve contact point of this ball crank lever, the two forces are acting. One is the weight of sleeve is mg, and second one is spring force S1. Okay, since we have the configuration like this, we have two balls and we have two contact points of the sleeve, so total sleeve force is acting here. The total sleeve force acting here is W. Okay, now since this two contact point, W is equally divided in both the levers, that is here W by 2, here is also W by 2. Okay, similarly the total spring force S1 is subdivided here as S1 by 2 and S1 by 2 on the second lever point. Okay, so the total force, the total spring and weight on the sleeve end is mg plus S1 by 2, that is half of total weight, total force. Okay, so now we will write a equilibrium of this lever. Considering equilibrium of lever in lowest speed, that is summation of all movements about point O equals to 0. So movement of this FC1 is FC1 into this distance x, and it tried to rotate in anti-clockwise manner, so I will take it as negative. And other is movement of this mg and sleeve force F1, which is clockwise, so positive, is mg plus spring force divided by 2 into the distance of the fulcrum and this weight, which is 80 mm, equal to the length y. So equals to 0, and there is no other force. That means the weight of sleeve and obliquity is neglected here, as we discussed in previous notes. So the epsilon is known to us. M is not given. So M we will consider as 0. So the value of M is 0. Okay. Epsilon is known, X is known, S1 we have to find, and Y is known to us. So we can easily determine the value of S1 by substituting the value of epsilon, X, Y, and all. The final value of S1 is 831 newtons. This is our first answer, that is the spring force in the lowest configuration. Answer 1. Okay, now we will consider this next configuration, and for this next configuration we will write the same equilibrium equation. So take this configuration with us. We'll move on the next page. Here you can see this configuration. Okay, and you can see here the epsilon is the force, centrifugal force acting on the ball, and mg plus s2. In this case the force is s2. Okay, the force is s2, which is acting on the sleeve end. There is no change except this x2 and fc2. So the moment equation is also same, that is fc2 into x is equals to, which is anti-clockwise movement, should be equal to the all clockwise movements. Clockwise movements are developed by mg and spring force s2 by 2. Again, since we are considering the equilibrium of one lever only, therefore this force is equally divided by on the both the levers used in the governor. So this distance is y. Again, m is considered as 0. So we can determine the value of S2 by substituting the value of FC2, which is P76, and X and Y is 120 and 80 mm respectively. You can put the values in mm because here mm will be cancelled out, and the value of S2 will come in newtons, which is equal to 1128 newtons. So this is our answer 2 of this problem. Okay, the first part, second subpart of first part of question. First part is completed. Now we have to determine the stiffness. Now for a stiffness, we can use this relation. For the stiffness, we can use this relation. But that's so what we do know about stiffness. You know the value of S2, you know the value of S1, you know the value of H. You can easily determine the stiffness by substituting the value of S. Using this relation, you can find the stiffness S2 1128 minus S1. S1 is 831 divided by 31 divided by H, that is 15 mm, that is 0.015 meters. This is in Newton. By substituting these values, for the values, we can calculate the S is equals to 19.8 Newton per meter. The value of stiffness of a spring is denoted by small s. Okay, this is the next answer. In this way, we can solve the problems based on Hartnell governor. Okay, if you have any doubt or queries related to this class, you can ask us. Thank you.